Hi, my name's Dr. Jonathan Hargreaves, and I'm just going to talk to you today about a study we did, a field assessment of air source heat pump noise, which was in collaboration with the UK Heat Pump Association. So we're part of the Future Homes Project Acoustics team. Just a little bit about that first of all. So the aim of the Future Homes Project is to accelerate adoption of low or zero carbon technologies through industry and academia collaborations. It tries to adopt a holistic approach to low carbon technology, so it's focused on all these aspects, so energy, air quality and acoustics in domestic housing, whether it be that new build or retrofit. It's funded by Innovate UK, so the total project, not just the acoustics, the whole thing was 3.54 million, and that was originally due to end in March 2025, but success of that phase prompted a £1.4 million additional 12 months extension, so that carries us up to March 2026. At time of speaking, it's currently September 2025. And this is going to allow us to do further case studies, work on impact for industrial partners, and advise policy and do further research. Some key acoustic focus is going to be on air source heat pump noise, and the kind of aims here are to help ensure air source heat pump noise does not become a barrier to their rollout, to develop best practices for measuring air source heat pump noise, and to investigate psychoacoustic effects, that is sort of the human response aspects of air source heat pump noise, how it affects people, which is what matters at the end of the day. So the team is led by Professor Antonio Torres-Martinez and myself, and then there's also Professor David Waddington working in an advisory capacity. Under us there's then another 6 researchers. It's quite a big team. But on to the field study, as I say, which was conducted with the Heat Pump Association, who were really pivotal in gaining us access to the site and use of the heat pumps and all that sort of thing. So what's the purpose of this? What's our aim in research questions? Well, our aim is to make quantitative measurements of air source heat pump noise in situ, determining that noise both at the homes where they're installed and at neighbouring properties. And this has been considered before, but we're interested in more than one air source heat pump, and this has been considered before. For example, this report by Apex Acoustics was commissioned by Nesta, considering kind of same sort of cumulative noise implications. But the difference there is that's a simulated study, and we really need to know if that's what happens in practice. And that study itself has some caveats in it. At the end it says that the modelling carried out here is based on incoherent sources. That means sources that don't interact with each other in any fashion acoustically, as is usually assumed in environmental noise calculations. And it says potential sound characteristics of a cumulative noise level due to air source heat pumps interacting with each other were not considered. So that's the kind of thing we want to be looking for here. And it goes on to say particularly the presence of beating for units with slightly different spectra may change the conclusions. So that's also something we want to look at. Is there beating or kind of tonal effects? So for us, what we're going to do exactly. So our main topics of interest in our research questions were to look at the cumulative effects of multiple air source heat pumps in close proximity. Can the combined level of multiple air source heat pumps be estimated by simply summing the sound power, as is common in environmental acoustics, or are there some low frequency interaction effects if these units are very close together? Additionally, we're interested in the micro certification scheme, MCS standards. Particularly these have changed, so we've moved on from MCS 020 in 2019 to 020A 2025. The calculation process has been updated and modified, and we can use this set of houses as a kind of check between the two, and just ask the question: does the compliance status of the air source heat pump measures change between the two versions of the standard? And it was the same site for both, but this was 2 separate phases that were actually conducted at 2 separate times. So onto the site. So again, first question is to choose the site. Again, there's some precedent for this in the work from Apex Acoustics. What did they choose? And they was a simulated study, but they chose some actual places to inspire the geometries that they simulated. And they chose this particular location in London, in Lambeth, and basically this was semi-detached or terraced properties with adjoined gardens, and it's assumed that the air source heat pumps would be located in the rear gardens. And that's basically what we're more or less assuming as well. That was the case in the test case we looked at, but we looked at new build. And the reason for that is it's much easier for measurement purposes than retrofit. And that's because it's unoccupied, there's nobody in any of the properties, and they're also all uniform. They haven't been kind of furnished and changed by the occupants yet, so it makes things a lot easier. One thing I will note on this figure before we move on is the distance between the houses, which was 20 metres, so that's kind of taken as being characteristic. So here's a CAD diagram of the site we studied, which I say the Heat Pump Association kindly negotiated us access to. And it's two pairs of semi-detached dwellings with adjoined gardens within a larger development, some of which was occupied, but these houses were still empty. And we numbered those 1, 2, 3, 4. There we go. And they are 17 metres apart, so kind of similar to what was assumed in the Apex study. They all have identical air source heat pumps, and they're located back. They're installed back to back on opposite sides of separating fences, which, you know, was one of the configurations we were very interested in, particularly with regards to possible beating or interaction between them. We kind of thought this was probably a worst case. You know, if we're going to measure it anywhere, we were going to measure it here. The fence itself was a 1.8 metre high closed board, and the air source heat pumps were situated on identical sized patios as per the diagram, with no particular vibration mount, so we don't think that's probably important because the patio itself was flag cemented down, so that's not going to be vibrating in any meaningful way. Finally, the gardens were grassed, so it's propagation over grass. In terms of limitations over the site, there's a few things. So first of all, the site isn't level. Now this perhaps isn't that unusual, but it's, you know, something that makes it unique. And in particular, the properties 3 and 4 on the top right of the diagram are higher than properties 1 and 2 on the bottom left. Additionally, properties 1 and 3 are also about 40 centimetres higher than their neighbours, which looks like it's been drawn in error, but it was actually how they were built. And you can see in the photos here that there's a stagger between the two houses. Now this also applies to the patios and the height of the air source heat pumps. So if you look at the air source heat pumps, some of them behind them have this 40 centimetre concrete buttress, and, you know, it's possible that might have an acoustic effect that affects directivity. We don't know. We'll see some differences when I show you some results from side to side, and that's one possible explanation, though it's unproven. And secondly, another limiting factor was it was near a busy A road, 40 mile an hour limit, and it was only 50 metres away. And this was a constant source of background noise, even into the night. We stayed quite late into the night to wait for traffic to die down, but there seemed to always be something in the far distance. There was some distant traffic noise, even if we screened for local pass-bys in the near field. So let's talk about phase 1 of the measurements, and just to remind ourselves, the aims here are to look at cumulative effects of multiple air source heat pumps in close proximity and ask the question, can the combined level of these two multiple air source heat pumps operating in close proximity be estimated simply by summing the sound power, and also are there low frequency interaction effects. So we're going to concentrate just on the gardens of properties 1 and 2 for this, in particular between air source heat pumps 1 and 2 down on the bottom left. And to answer that top question, then we're going to try and answer that directly. So what we'll do is we'll run one of the heat pumps, turn the other one off, and we'll measure the sound pressure level that arises from that. Then we'll flip them round, we'll turn on heat pump 2, turn off heat pump 1, measure the sound pressure level again. So those are two individual measurements, which are kind of like what if you did the MCS standard for heat pumps individually, that's what that would predict. In terms of the cumulative aspect, well, let's turn them both on and we'll measure the sound pressure level with them both operating. And then we're going to compare that to, you know, if we did basically a power summation, a sound power summation on the two separate measurements, which is how a standard environmental noise assessment would generally do this. You know, you just tend to assume that sound adds incoherently according to its power. And, you know, is that a reasonable assumption for heat pumps that are very close together? That's what we're asking, and we're going to basically test that simply by comparing these two things with each other. You know, and then that's going to lead to potentially some recommendations, maybe a correction if there are sort of systemic problems. Limitations of the methodology here are that it basically assumes the air source heat pumps always run in the same state when they're active, which isn't often the case. You know, they may change as time evolves, and it's quite difficult to control exactly what an air source heat pump does while you're just testing it. And then also just to ensure what we call a good signal to noise ratio, so that the air source heat pump noise needs to be plenty louder than sort of background and traffic noise. Otherwise, the two separate measurements on the left both include the background noise, so that's kind of getting doubled in the power summation. And if that's quiet enough, it won't make a difference. But if it was as loud as the air source heat pumps or similar, then it would skew the results. So we need nice, quiet background noise. So how do we do this? Well, we tried to do more than just a simple sound level meter. We tried to get some bit more information. So we had a whole arc of microphones here. You can see them on the screen. That's 2.5 meter radius, and there was 9 microphones on this at 20 centimeter spacing. And the aim here was to capture the directivity of the sounds emerging from the 2 air source heat pumps, so their own natural directivity and the effect of the orientation, but also the effect of the fence and potentially the effect of the garden height mismatch here as well. Additionally, we also did a tonality assessment on the data, and we looked at did a fluctuation strength analysis to look for beating effects. So let's just look at some of the background and individual sound pressure levels first. So with neither heat pump on, this was the background level that we saw. So nice and quiet. This is late into the evening, and also below the MCS thresholds reasonably comfortably, so that seemed to be okay. Then we turn air source heat pump number 1 on the right hand side on, and we can see that the sound pressure levels, these are all bars of sound pressure level, A weighted, versus the microphone angle across the arc. We can see that those will pop up on the side of the fence where the air source heat pump is, which is basically what we expect. And you can see here that we've got quite a good signal to noise ratio from one side to the pump fence to the other, and we're also well above that background noise on the right hand side. So this is looking good. Turn that heat pump off, turn on number 2 on the left hand side, and we get sort of something quite similar to more or less mirror image, little differences, but basically the mirror image effect, which is what you expect. Then we need to operate them both together. So let's go to the background and look at them both operating. So now we turn them both on. And this is what we see. So we see fairly uniform SPL more or less across all the microphones, regardless of angle. And now we have the 3 pieces of data we need for our methodology in yellow, blue and orange, and that corresponds to the yellow, blue and orange on this slide. What we haven't seen yet is the power summation in purple of the orange and blue. So that is what you'll see in this graph here. It's got a few more things on it, but the blue, orange and yellow bars are all the sound pressure levels you've seen already. The only added one is the purple, which is derived by doing a power sum on the blue and the orange. And we're interested in, do the yellow and the purple agree? And they are pretty close. So there are some differences of a couple of dB just on the right hand side of this graph. So let's just look at the difference between these. We're going to look at the yellow measured SPL minus the purple predicted SPL in this graph here, just difference versus angle. And what we, in terms of how to interpret this, close to 0 is what we expect, based on standard environmental noise calculation methodologies. Negative values are kind of, I suppose, good from a planning perspective, because it means that you're not going to install these things and they would actually be quieter than they predicted, so that would be good. Whereas positive values will be kind of classed as bad from a planning perspective, because it means you did the calculation, then you installed the thing, and it's actually noisier than you thought it was, which therefore is going to potentially give annoyance or non-compliance. So positive is what we want to avoid here. That would indicate there's something going on that's not that straightforward. But we actually see that there isn't that much difference. These on the left hand side are all close to 0, so that's absolutely as expected. There is some natural variance here due to background noise and the methodology inevitably. There's a slight systemic bias on the right hand side, but when we revisited these recordings, we could hear that actually the heat pump number 1 had kind of changed its operating state ever so slightly, unfortunately, and these have kind of popped up a little bit due to that. In the report, there's a second version of these comparisons with some different operating modes, which you can also look at. But overall, nothing really unexpected here. It seems that the standard environmental noise power addition approach seems to be okay. On to the tonality assessment, for this we followed the methodology outlined in Annex D of BS 4142/2014 plus its annex, which is also referred to the joint Nordic method. And this is based on the psychoacoustic concept of critical bands and masking, that you'll only hear a tone if it sort of pops up above the level of the neighbouring sound, which is the same thing that exploited in MP3 to make file sizes smaller. If a sound of a certain frequency could be masked by other energy in that frequency band. So the key result is that we had prominent tones, and there's a few more listed in the report, but here I'll just focus on two. There was 110 Hz detected for both units, and it's detected on both sides of the fence, so also on the side with the fence where the unit's not running. That's a pretty low frequency tone. It's sort of round about what you might hear some mains hum harmonics at. We also detected 14 kHz very strongly for this particular unit. Don't quite know the origin of that. It's quite a high, almost slightly whistly sort of sound, this, and that was very much just on the side of the fence that you expected. Just to explain that prominence thing again, here's a little plot just showing an extract from some data where you can see the tone frequency bins in red just exceeding the fit in blue through the neighbouring spectra. So that's how this prominence is assessed. How much above the neighbouring spectra is it? Right, so let's have a look at what those tones are doing. So we're going to plot some directivity plots. So again, we'll start off with just air source heat pump number 1 on the right hand side running. And this is the plot of the SPR. Now this is actually a polar plot, so the radius here is sound pressure level going outwards from 0 to 35 dBA. And the blue line is 110 Hz, the orange line is 14 kHz. So that's the pattern we get for those two, whereas if we switch over and switch the other heat pump on, then we get this other pattern, which is almost symmetrical but not quite. And this area here in orange is kind of what we expect to see. We expect to mostly be seeing energy, on the side of the heat pump that's operating, and that is true for the 14 kHz tone. But the 110 Hz tone has a little bit of a notch, sort of vertically upwards. But then on the other side of the fence, it's just going straight through, and it's not really any quieter than it is on the side of the property where the air source heat pump's installed. So this is going straight through to the neighbour without any real attenuation by the fence, which is potentially quite important. So in terms of the findings from phase 1, the power summation, sort of what you call logarithmic dB addition, was seen to be adequate for this case, with only small differences which are explainable by things like background noise or the change in operational state I just mentioned. Perceptible tones were detected both at low and high frequencies, and some of these low frequency tones show minimal attenuation by the wooden fence, so was present strongly at the neighbouring property. Some beating was thought to possibly be heard by investigators, but analysis of the measured data didn't show anything above any perceptible thresholds. And to be fair, this was measured in the day when there was, heard in the day when there was some plant machinery operating not very far away, and it was also heard only kind of down behind the air source heat pump, which is not a very realistic listening position. Further work on phase 1 is mostly about trying to understand the fence better, both its attenuation and what higher performance designs might look like. With that in mind, I'm going to take a slight deviation from the fieldwork now and talk a bit about some laboratory pilot studies that we did, and looking at some fences in our laboratory in Salford in the acoustics labs. And and the question here is, how does the sound power transmitted over a fence compare to that transmitted through it? And this is important because most legislation for looking at noise barriers assumes that the noise barrier is impenetrable to sound, and that is not the case for this fence, as we'll see in a minute, and will make a big difference to how one should actually predict its effect when doing these modelling and planning calculations. So the methodology for this, we have a fence, as you saw. On the source side of the fence, we didn't use an air source heat pump. We actually used a dodecahedron sort of omnidirectional loudspeaker as a common in environmental noise and acoustics. But this didn't really quite go low enough in frequency, so it was supplemented by a subwoofer, which you can see on the right hand side of that picture, which basically took the excitation down to 28 Hz. So this comfortably covered the range in which we're likely to get much output from an air source heat pump. Difference is that there's no flow going on, no airflow. On the receiving side of the fence, we have two high precision instruments. One is a laser Doppler vibrometer, and this, by shining a laser beam at the fence, can measure the vibration of the material at a certain point. So assuming here that the fence is relatively airtight, which this one seemed to be, there was a few holes, but we plugged them up. So we're looking at how the material moves, which would be the kind of the method of sound transmission through a lightweight fence. And basically this laser scans over the surface, takes a load of sequential measurements, and then creates an animation of the sort you'll see in a minute. And then secondly, we did another scanning measurement, which was scanning intensity, and the funny light you can see then the stick is actually just from a tracking LED, which is being tracked by a camera. So again, you scan this round, in this case manually, and measure the sound power or sound intensity, sound power density that's coming through the fence. And this is a bit more sophisticated than a microphone, which only measures pressure. This also is called a microflone, and it also has a tiny little anemometer in it, a little hot wire anemometer, MEMS device, and that can actually measure the movement of air due to sound. So we're getting both the pressure and the movement of air, which is what you need to calculate the sound power transmission close up. So first of all, to the laser vibrometer results, what that found for its vibration, and here's some patterns from that. And at the low frequencies, we can actually see distinct peaks in the response, as you'll see in a moment, where there's certain particular patterns that the fence is very much acting in. And the lowest few of these have quite distinguishable modes, sort of mode shapes we call them in acoustics, vibroacoustics, this is quite normal for panels that you get these sort of patterns, a bit like a Chladni plate, perhaps, if you've ever seen one of those, that sort of thing. The difference here is that, of course, the fence is constrained by its posts. So it's moving in certain patterns, and they're particularly strong at certain frequencies. Later on, you can see that these kind of gobblin frequencies get more complex, and the one at 123 Hz ends kind of beginning to get a bit messy because there's a few different patterns probably overlapping. If you look at the average panel vibration spectrum, the average energy over that scan area versus frequency, we can see all this. So we can see that there's various kind of peaks. We'd say it was modal below 100 Hz. What you get in terms of vibration response varies quite a lot from frequency to frequency, depending on whether the frequency of excitation happens to match the frequency of one of those sort of mode shapes and vibration patterns the panel likes to move with. But then when you get higher up, it all gets a bit chaotic. There's a lot of overlapping behaviour. There's not really any distinguishable individual peaks anymore. And then once we get past about 400 Hz, we see that actually the sound transmission through it begins to tail off, and we're getting some reasonable attenuation going on. So that's going to tell us the sort of nominally, where the fence is moving, and therefore a sound could go through it. In terms of this as a contribution analysis, well, I'm not showing any full scans of what's going on here, but we kind of did an overall summation of the sound power going over the top versus through, and this was the intensity going over the top versus through, and so through the fence is the dashed line, and then over the top is the solid line, just scanning and separating the power that we scanned, the areas we scanned over, into these two sections. And just to give a comparison, we also went and screwed 18mm plywood onto the fence afterwards to add the mass and make it a bit more solid and a bit more impenetrable. And that's the orange lines. And as you can see from the dotted line, that's reduced the movement and therefore the amount of sound energy coming through the panel. And crucially, with 18mm plywood facing, the sound transmission through the fence is about 6 dB down from the sound transmission over the top. So that is about a quarter of the power density. And that essentially means that this is not too significant. There is power coming through it, but it's not that much. If you were to ignore it, the majority of the power is coming over the top, which is what's assumed in most planning calculations. Whereas for our thin wooden fence, we can see that at the low frequencies, certainly below about 400 Hz, there's as much energy coming through the thing as over the top, so you really can't ignore that. It's going to be quite significant. And the detail of that is going to be very dependent on the exact frequencies that we're looking at, as we saw from the laser Doppler vibrometer results. And it's been pointed out that it's going to be very dependent on fixing, structure, wood type, wood humidity, all sorts of things. So this is just one case, it's a pilot study, but nonetheless it shows that there is some implications for barrier attenuation and Q factor, but definitely more research on this is required. So I hope that's an interesting diversion. That's the sort of thing we're trying to do in our labs to understand this better. So back to the field study and back to now to phase 2. Same set of houses, now we're using all 4. And the idea here was to use a case study for comparing the 2 micro certification scheme retrofit standards, 2019 and suffix A in 2025, to each other, and to see if they agree in terms of their with each other and also to measurements. A kind of problem here, the idea was that all these 4 heat pumps would run. Unfortunately, we had some trouble when these measurements were done. The site had already been handed over, which meant that access to the houses was no longer possible, so we couldn't directly control what the heat pumps did. So we were just the heat, they were all supposed to be active, but we just sort of took what we got in terms of when they actually ran. And unfortunately, that wasn't very much. Only one of them ran at all. So we'd wanted to have all combinations of all 4, but in the end we only got 1. So we have that heat pump to 4 ground floor kitchen windows and 4 first floor bedroom windows. And the reason we did the kitchen windows is that MCS 020A in 2025 changes the definition of habitable room to be include a kitchen diner. So technically these are habitable now. On that point, this is new build. MCS is for retrofit. They wouldn't have been applied here when in the planning. So what we're showing here is not showing there's something wrong with this site. It's just using it as an exemplar for those standards for retrofit planning. And here's a few measurements just showing some of the different microphones. You can see some in the middle of the kitchen windows or in the middle of the bedroom windows. You can see some near the heat pumps, which are just for the purpose of monitoring exactly which heat pump was active, which was only 1. There was some on the fences as well, which were meant to be there for sort of sound path analysis, but we didn't really use those because only 1 heat pump ran. In terms of the temperature and humidity, the temperature was about 5 degrees most of the way through the evening. There's actually 2 time periods here. There's one at night, and then there's also early in the morning. We came back early in the morning hoping the second heat pump would run a bit more. It didn't. Well, it ran once, but still none of the others did anything. And you can see the humidity there as well, which varies, typically in the 80% somewhere. So in terms of application of the MCS calculation, these were used as a case study for that. And despite changes in the calculation process, the 2 assessment methods yielded identical compliance statuses at all the assessment positions. So the sound pressure levels for assessment positions of the next door property, both the kitchen and the nearest bedroom windows, failed to meet the 40 dB limit stipulated by the 29 version and the 37 dBA limit stipulated by the current version when processed appropriately. In contrast, the properties across the gardens were compliant for both versions, so no issues there. So this suggests, as one might assume, that the noise to the nearest neighbour is often likely to be the most challenging, even if the more distant properties have line of sight. In terms of the measured sound pressure level versus the calculations, the operating heat pump, which we didn't have really control over, but just monitoring it up close, we could see that it moved through 2 states, and that the SWL, the sound power of those, the difference between the 2 states matched the difference between the maximum level operating state, which was used for the MCS 2019 calculation, versus the ERP level, which is using the 2025. So this is quite convenient. It allows a comparison between measurements and both MCS calculations. But there's a really important caveat here, is that the true sound power is unknown in both cases. Measuring sound power of air source heat pumps in the field is very difficult. We actually did do some work of it on phase 1 actually, but it wasn't feasible to do in phase 2. So this is only illustrative. We don't really know what the sound power of this is. Anyhow, here's what we found. So these are graphs are showing the measurements in the grey bars, the sound pressure levels vertically versus the mic positions. There's a bit of a legend on the right hand side there. KW1 is kitchen window, BW is bedroom window, and we've got the three properties, 1 being the nearest neighbour, 2 being the one that has the active heat pump, and 3 being across the garden. And these being for 2019 are actual sort of absolute full sound pressure levels I've measured. So we compare these to the 42 dB threshold, and you can see that generally things are in reasonable agreement. The green dots are the MCS calculation results, which in some cases match it very closely, in others a little bit less so. Perhaps the most interesting thing here is that at the nearest neighbour, property 1, so BW1 and KW1, the green dots from the MCS calculation say that it's over the threshold and not compliant, whereas actually the measured sound pressure levels were compliant. So that's interesting to see. Though specific, I should add, to this particular case, and we don't know exactly how the heat pump was operating. If we go into 2025, it looks at what is the actual sort of specific sound pressure level of the actual heat pump unit itself without the background noise. So for the measurements here, we actually had to subtract the background noise off the measured sound pressure level to get these graphs, and then we're comparing those to the MCS threshold. So we have the measured levels on the green dots there. The threshold's reduced to 37 dBA because of this as well, because we're looking at a slightly different quantity. And you can see again reasonable kind of agreement. The green dots for property 3 aren't on the graph because they've disappeared below 30 dB somewhere. For that property, actually, the levels are still about 30 dB because that's the background noise floor of the site. So we can see that for property 2, the levels are fairly accurate. For property 1, again, the dots from the calculations say it's not compliant, whereas our actual measured levels were compliant. So that's interesting to see, but again, specific to this particular example. Can't really generalise having any measured one. So phase 2 findings. So no change in compliance status between the 2019 and 25 versions of the MCS calculation protocol for the specific case evaluated in this study. The noise limits for them were seen to be fairly good agreement with measured sound levels, so there's some slight differences I just explained. However, the barrier fence attenuation from phase 1 remains a concern. And this is particularly for the calculation, this has some effects because there's another thing called sound power enhancement from reflecting surfaces called Q factor in the calculation. And if you've put a fence there that's actually letting quite a significant portion of sound through it by vibration, then that really bodes the question of, is this, to what extent is this really a reflecting surface if it's also letting a lot of the sound energy through? We also have a problem. The air source heat pump directivity, literally its own behaviour, is unknown, and there's no real robust or accepted way to characterise this in the field. There's some research work, and we've done some ourselves. There's no accepted method. So further work here really is to do a survey of additional sites. We're planning that for Q4 2025. We're just organising all that at the minute. And further modelling and laboratory measurement of fences is planned, though is subject to funding. So thank you very much.